Okay, exam 1, fall 2016, physics 101. A bus contains a 2,000 kilogram flywheel. A disc has a mass of 0.5 meters radius and has a total mass of 10,000 kilograms. Calculate the angular velocity the flywheel must have to have enough energy to take the bus from rest to a speed of 20 meters per second. And you're assuming that all of that rotational kinetic energy goes into the energy of the bus. So this was an OpenStax question. Some of you probably recognize that. It's been changed a little bit. In the OpenStax question, only 90% of the energy went into the bus. But just to make it a little easier, I just said all the rotational energy, that's 1/2 I omega squared, is going to translate into the kinetic energy of the bus. So this is what our equation is going to look like. The rotational kinetic energy of the flywheel goes into the energy of the bus. So I have 1/2. Actually, let's just get rid of these halves because they cancel out. Divide through both sides by 1/2. My I for a disk is a cylinder, 1/2 of the mass, that's 2,000, times the radius, which is 0.5 meters squared. That's I. Now omega is what I want to know. The mass, that's the mass of the bus, 10,000, times the speed of the bus squared. All right, so this is 1,000, this is 250 omega squared, this is 400, 4 million joules, that's how much the bus has. And then if we calculate this, it's the square root of 4 million over 250. And I get 130 radians per second. So B is the right answer. Two objects have the same angular momentum. Object 1 is spinning, object 1 is spinning, object 1 is spinning twice as fast as object 2. So let's think about this. They both have the same angular momentum. That means the product of I1 and omega, I1 omega 1 will equal to I2 omega 2. They both have the same angular momentum. But I know that omega 1 is twice omega 2. And I know then, therefore, that I1 is 1/2 of omega 2. Now, then I can write the energy of the first disk is 1/2 I1 omega 1 squared. That's 1/2 I1, which is 1/2 of omega 2, or excuse me, this should be I2, excuse me, 1/2 of I2, and then omega 2, which is twice omega 1, which is twice omega 2, and that's squared. So here I have this 2, which is squared, so I get a factor of 4, and I get a factor of 1/2, so I get overall these two give me twice E2. That E1 is twice of E2. E2 was 10. That means E1 is 20. Now you could have probably seen this because it said that object 1 is spinning twice as fast as object 2, and we've seen some problems like this in class where if it's spinning faster but they have the same angular momentum, that means that it has a faster speed but a smaller moment of inertia, but because omega is squared, then it contributes more to the energy. So you could probably intuit that the energy of object 1 is going to be bigger. So you could have gotten rid of this answer, and this answer, and just leave you with A and D. And then you need to figure out, well, which of those is correct. All right. Number 3. We want to rank the moments of inertia. Well, gosh, let's first ask ourselves, where is the biggest moment of inertia and where is the smallest moment of inertia? About this axis is where we're going to have the biggest moment of inertia. So I get rid of that one, and that one. I know it's that one because I have the largest moment arm for the most mass for this one. So here I have a lot of mass over here and out here. The biggest moment arm for the most mass. So A definitely has the biggest moment of inertia. And then C has the smallest moment of inertia because I have the smallest moment arm for there. And notice both of these have C. So now the question comes down to, is B bigger than D or is B equal to D? Well, these are symmetrical, so B is going to equal to D. So E is the right answer. All right, this shows a disc with a radius equal to 2 meters, and it has a mass of 3 kilograms. And then there's also a mass attached to the disc. This is kind of like the problem that we worked with the kid on the merry-go-round. So I want to know, what is the moment of inertia? The moment of inertia is going to have two components, the disk plus the particle. All right, the disk, which is a cylinder, is 1/2 mr squared. And the particle is going to be just mr squared. Now we need to be careful that this is the mass of the disk and this is the mass of the particle. Unfortunately, they have the same radius, so I won't distinguish. But if they didn't, you'd have to distinguish between those two. So this is 1/2 the mass of the disk, that's 3 kilograms, times the radius, which is 2 meters squared, plus the mass of the particle, which is 4 kilograms, times the radius at which the particle is rotating, which is 2 meters squared. So that's 6 plus 16, which is 22. All right, that first page was a doozy. Let's go into the second page. A bar has a moment of inertia of 8 kilogram-meters squared and is rotating at 2 revolutions per second in the counterclockwise direction. It engages with a flywheel, which is rotating in the clockwise direction at 4 revolutions per second. It has a moment of inertia of 16 kilogram-meters squared. What is this new speed after they engage? So I know that my initial angular momentum is equal to my final angular momentum. And my initial angular momentum is 8 kilogram-meters squared times 2 revolutions per second. That's counterclockwise, so it's positive. And plus 4 kilogram-meters squared, or excuse me, 16. 16 times -4 revolutions per second. That's going to equal the final moment of inertia, which is 18 plus 6, or 24, times omega final. This is 16 minus 64 divided by 24, and that's equal to -2 revolutions per second. It's negative, so it is clockwise, and A is the only answer that fits anyway. Two 20-kilogram children are sitting on a merry-go-round that's rotating at 0.1 radians per second. You have one child at 1 meter and another child is 0.5 meters. What is their combined angular momentum? Well, L will equal to I1 omega 1 plus I2 omega 2. So we need to figure out their moments of inertia, and they both have the same speed. So omega 1 and omega 2 will be equal. My I1 is going to be 20 kilograms times the radius squared, that's 1 squared, plus I2 is going to be 20 kilograms times the radius squared, 0.5 squared, 0.5 meters. I'm going to multiply all of this by omega. So see, I just factored out that omega since it's common to both of them. So this is 20 plus 20 times a quarter, that's 5, times omega. Omega is 0.1, so that's 25 times 0.1, or E for number 6. Or consider this rod. What is the net torque? Okay, well over here I have a clockwise torque, so it's negative. Over here I have a counterclockwise torque, so it's positive. And here I have no torque at all because it's at the axis of rotation. So my net torque is going to be negative 20 times 2 plus 10 times 2 meters. That's this distance, and the 2 meters over here too, times the sine of 30. And so that is negative 40, 20 times a half, plus 10, 30 Newton meters negative, so it's clockwise. Now, after 2 seconds, what is the net torque acting on the rod? Well, first I have to know what is the moment of inertia of the rod. That's 1/12 mv squared. That's on your equation sheet. That's 1/12 of 3 kilograms times B, which is 4 meters squared. That's 3 times 16 is 30, 48. That's 4 kilogram meter squared. Now I say alpha is torque over I. Alpha is torque over I. That's from Newton's second law. So I said that my torque was 30. It's negative 30 actually. Divided by 4, that's negative 7.5. That's in radians per second squared. And then omega is equal to alpha times t. That's one of our kinematics equations. 2 seconds, so it's negative 7.5 times 2 seconds, and that gives me 15 radians per second. I'm just looking for the magnitude of it, so we're not worried about direction. When will an object continue spinning at the same angular velocity? When the net torque is 0. When it's non-zero, it's going to accelerate. When the angular acceleration is positive or when it's negative, it could be either speeding up or slowing down depending upon what is the direction of its velocity. And when the net force of the object is 0, not necessarily. The net force can be 0 and it still be spinning. So for example, if I have an object like this and I have a force right here and a force right here, the net force on that is 0, but the net torque is not 0 on that object. So not necessarily if the net force is 0. Okay, I have a rectangular boat, 2 by 1 by 2. What total mass can it keep afloat? Well, the weight of the boat for it to be afloat has to equal the buoyant force of the boat. That's mg, density of the fluid, volume of the boat times g. Now my g's cancel, and I'm looking for the total mass of the boat. So it's going to be the density of the fluid times the volume of the boat. Density of the fluid is water in this case, that's 1,000 kilograms per cubic meter, and the volume of the boat is 2 times 1 times 2, or 4 cubic meters. So I can get 4,000 kilograms. Boat carrying a large chunk of steel is floating on a lake. The chunk is then thrown overboard and sinks. The water level in the lake drops. Why? We saw this question in our concept test. So what is the explanation though? We know the level drops. The reason is that the steel displaces more water when it's in the boat than when it's submerged. When it's submerged, it only displaces its own volume in water. Or in volume, it only displaces its own volume. When it's in the boat, it displaces a volume of water that has the same weight as the steel, and since the density of water is less than the density of steel, then it's going to displace more water than the volume of the steel. Water flows through a pipe, the pressure is 2,000, and the water flows at 1 meter per second. The pressure in the next section of pipe drops to 1,000 pascals. Oh shoot, I'm sorry. What has happened to the pipe? Well, so if the pressure goes down, that means that the speed has gone up. And for the speed to go up, you have to have a pipe by the equation of continuity that gets narrower. So number 12 is A. 13 is a similar question. I'm going from a 2 centimeter diameter to a 1 centimeter diameter. So the diameter is 2 centimeters. Be careful, I'm talking about the diameter, not the area. And now I'm going down to 1 centimeter. So my area has decreased by a factor of 4. Area has gone down by a factor of 4. I have now 1/4 the area because my radius is half what it was originally, and area is pi r squared. If I decrease r by a factor of 2, the area decreases by a factor of 4. If the area goes down by a factor of 4, that means the speed goes up by a factor of 4. So it was 0.02, and so it should be now 0.08. I'll have to go back and fix that one, but it should be 0.08. I'll fix the options on that one. Probably what I'll do is I will make this, instead of 0.02, I'll make that 0.01. So that's how we'll see that in the test. All right. So that's number 13. A straightforward method of finding the density of an object is to measure its mass and then measure its volume by submerging it in a graduated cylinder. Y'all did this in lab. Material displaces 93 milliliters or cubic centimeters of water, and it has a mass of 1,800 grams. What is the substance? Okay, well the density then is 1,800 grams divided by 93.3 cubic centimeters. Remember, milliliter is a cubic centimeter. So 1893.3, and I get 19.3 grams per cubic centimeter. And remember, like, the density of water is 1 gram per cubic centimeter, and it's 1,000 kilograms per cubic meter. In a similar way, this density is 19.3 grams per cubic centimeter, and it's 19,300 kilograms per cubic centimeter, or cubic meter rather. You can go through the unit conversion if you want, but I find that a lot easier, just to remember that the density of water goes from 1 to 1,000 when I'm going to SI units. And so you just multiply by 1,000 to get it in SI units. And if you look on your table, you'll find that that's the density of gold. Pascal principle says that, let's see, it's not that, that's Bernoulli's. It sort of looks like it should be that, but that's not really true. A small input force does not always cause a large output force. It could cause a smaller output force, or the same force. That's the equation of continuity. This is Pascal's principle, that a change in pressure at one point is felt at every other point in the fluid, and that is Archimedes' principle, E. So the answer is D. This figure shows the essential parts of a hydraulic brake system. There's the area here, so 2.4 to 9.6. So my area has increased by a factor of 4. I've gotten a bigger area. That means that my force is also going to be increased by a factor of 4. So I had 16 newtons. Now I will have 64 newtons. We can work this out. I would say F1 over A1 equals F2 over A2. I'm looking for F2, so I would have 16 over 2.4 equals F2 over 9.6, and then I would find that F2 has to be 64. This manometer is measuring the pressure P. The known pressure is 1 atmosphere, so I have 1 times 10 to the 5th over here, and the liquid is mercury, which you can look on your table, has a density of 13,600 kilograms per cubic meter. And I want to know this pressure. This pressure is bigger than this pressure because it's pushing that fluid down, and so P is equal to P naught plus rho GH. And P naught is 1 times 10 to the 5th. Rho is 13,600 kilograms per cubic meter. That's 10 meters per second squared. And then H is 0.1. And so I get, let's see, these just cancel out, go to 1. They don't cancel out, but they multiply to give me 1. And so I get 113,600, which is just 1.1 atmospheres. Notice the options are all given in atmospheres there. All right, so that's right. Estimate the pressure a person standing on 1 foot exerts on that foot. Well, gosh, what is the area of your foot? Well, your foot's about 30 centimeters by 10 centimeters, and so that's about 300 square centimeters. And if I convert that to square meters, which is what I need to do, I know that there are 100 centimeters in 1 meter. I have to square that, and so 300 divided by 100 squared is 0.03 meters. So that's one thing. You sort of need to estimate the area of your foot. 12 inches is about 30 centimeters. If you're off by 10 centimeters, it's not going to affect you that much. You'll still be able to pick out the right answer. The weight of a person is about 700 newtons, 0.03 meters squared. I get 23,000, so A is the right answer. For water, which state is the most dense? Well, you think the solid, but as we talked about, ice actually floats in liquid water, which is a nice thing about water, and is why we're able to live on this very wet planet. So B is the right answer. 10-meter rope has a diameter of 0.02 meters. When you pull on it with a force of 1,000 newtons, the rope stretches 1 centimeter. What is the Young's modulus? All right, so F over A equals Y delta L over L. I'm looking for Y. So it's going to look like this. My force is 1,000 newtons. A, well, I'm going to have to figure this out. That's going to be pi times the radius squared, which is 0.01 squared. L is the length of the rope, 10 meters, and delta L is 1 centimeter. That's 0.01 meters. And so let's see, I have 10,000 divided by pi 0.01 cubed. So I get 3.2 times 10 to the ninth. Alright, so B is the right answer there. Alright, rigid container has this volume, has this number of moles of gas. It's at this temperature, but beware your units, okay? This temperature is actually equal to 293 Kelvin. You need to be able to, that's just a good temperature to know in Kelvin, actually 20 degrees Celsius. Alright, and then I do my ideal gas law equals nRT. I want to know the pressure. So pressure is nRT over V. So that is 30. R is 8.314 joules per mole Kelvin. Divided by our T is 293. Divided by V, which was 0.5. And that works out to be 1.5 times 10 to the fifth Pascals, which is the same as 1.5 atmospheres. Watch your units on that one. Which has a greater number of atoms, a mole of nitrogen or a mole of oxygen? Give all this junk, but you don't need any of that stuff because they both have the same. A mole is a mole is a mole. You have a steel rod that's stuck in a concrete block. Which of these is the best solution to remove the rod? Look on your table and you'll find that the coefficient for steel is less than the coefficient for concrete. All right, that means if you heat up steel, it's going to expand at a slower rate than the concrete. And likewise, if you cool it down, it's going to shrink at a slower rate than the concrete. So imagine my concrete block here and my steel. This is steel, this is concrete. It's stuck in there. What can I do? Well, if you cool the steel rod and the concrete block, they'll both shrink. But the concrete block will shrink at a faster rate because it has a higher coefficient. If you heat the steel rod, it's just going to stick more. If you cool the concrete block, the hole is going to get smaller. So that's not right. If you heat the steel rod and the concrete block will increase size at a faster rate than the steel rod. So D is the right answer. And 20 degrees Celsius is the same as 70 Fahrenheit. It's room temperature. Two objects have in thermal equilibrium. It is necessarily true that they have the same temperature and that only. And Dr. Young thinks I'm awesome. Yes, yes, yes. All right. So